Welcome to MECH314, Introduction to Fluid Mechanics. We are starting Chapter 2, and in this chapter we deal with fluid statics. And we will talk about what we mean by static fluids, and then we will derive the hydrostatic pressure distribution, and then apply that to manometers, and eventually to finding the forces on submerged objects such as surfaces and three-dimensional objects, and we will leave the last part of this chapter in White's book until a later stage in this course. So, by definition, a static fluid does not sustain any shear between its fluid elements. So if you look at remember we did this slide before, if you look at a solid under deformation and you take a free body diagram, you take a cut and expose the stresses inside the object, on a Morse circle, on a normal stress, shear stress circle, you'll see that you can have both a normal component of the stress and a shear component of the stress. However, by definition, a static fluid cannot sustain any shear. So a static fluid only has normal stresses. So we're only working on this normal stress axis. The shear stress component of any fluid element force is zero, no shear stress. So the only force becomes the normal stress, which we call the pressure. And we've also learned in the previous chapter that pressure is a thermodynamic property, and it helps us tell what the state of the material is. And when we're dealing with gases and liquids, we do have internal pressures. So pressure has units of Newton per meter square. So it's a force per unit area. It's a stress. By definition, the pressure is a compressive stress. So it's always pointing towards the area. So it's force per unit area, so it's always the force is always pointing towards this area. That's what we mean by compressive. And it's always perpendicular. So if you remember those two, these are the two primary basic fundamental pieces of information that we will use throughout this chapter in our solution of fluid problems. One, the pressure is compressive, and two, it's perpendicular. And as long as we have a static fluid, we don't have any shear stresses. So the only interfluid force is the pressure force. So if you take a fluid element like so, this is point. So this is a cup of water, for example. And this is a point element, and I've picked it to be weightless, so it's so tiny that it's weightless. It's a static fluid. So since it's static, the fluid element doesn't go anywhere. But I know that there are fluid elements all around my blue element here, and each one of those elements contributes a force per unit area that is compressive and perpendicular, and that force is the pressure. So this is the pressure distribution around my element, my weightless fluid element that's over here, and all the pressures are symmetric and of equal magnitude, so they have no net contribution to a force. So my fluid element sits where it is, and it stays static. And I don't have to pick a point element. So now this is more a demonstration of a control volume, a triangular control volume. It's still in the same cup of fluid, and it's still a static fluid. So this imaginary control volume is not going anywhere, it's not moving. And to demonstrate the pressure is compressive, so you'll see on each one of those three surfaces, the pressure is compressive, pointing towards the surface, and it's perpendicular. And on the vertical surface, the pressure force is horizontal, and on the horizontal surface, the pressure force is vertical. And you see, we're not drawing the pressure force from the inside of the object, we're drawing it from the outside, because what we're drawing here, the pressures Px, Pz, and Pn are the forces of the surrounding fluid on my fluid element that I am looking at over here. So the surrounding fluid acts in a compressive fashion, and the force acts perpendicular to the area. So now we look back at our point element right over here, and we said that there is it's in a cup of water at a depth h from the top of the cup, which is open to the atmosphere or some pressure. And one of the interests that we have is, what is the magnitude of this pressure when we're in a fluid of density rho and submerged in a height h? So one easy way of doing this is to consider a control volume. One side of the control volume is at the level h, and the rest of the control volume is a cylinder. So I started really by drawing this line right over here, which is where I want to find the pressure at, and then I completed a control volume, which is the blue line or the blue cylinder that's over here. That cylinder has a cross-sectional area A and a height h. So if my fluid is static and this cylinder will subsequently also be static, the fluid is not being mixed or anything, it's just sitting there, then it should be under static equilibrium in all three dimensions, in the x, in the y into the page, and in the z. That's the perpendicular direction. So if I do a summation sigma f z is equal to ma, then I should expect, I start with the notion that my fluid is static, so I don't have any motion, and there's no displacement, no velocity, and no velocity variation with time. That is, there is no acceleration. So I have my summation sigma fz, the forces, all the external forces and body forces acting on this blue control volume will be equal to 0. So sigma fz equal to 0, and what are the forces acting on my system? I have the pressure acting on this area, and I'm taking the z component of the forces. I'm not interested in the horizontal force balance, I'm only interested in the vertical force balance. So there is the pressure P times A gives me a force pointing upwards, and the weight of the control volume points downward. So that's pretty much it. So the weight of the control volume is counteracted by the pressure times the area at the bottom. And if so, what is the weight of the fluid? It's the volume of this fluid, which is the area multiplied by h. That gives me a volume. Multiply the volume by a density, you get a mass, and multiply by the gravitational acceleration, you get a weight. That's your W. So W equal to P times A. So the A cancels out, and you get a relationship between the pressure and the so that's your hydrostatic pressure force, because it's due to the weight of the fluid height above that level, that point P. And if I want to be more accurate, I actually said at the beginning that we have atmospheric pressure or some kind of pressure, P0, acting here, so I have to really include it. So really it's not just the P, it's the P minus P0. So this is the relationship that governs the pressure at the point submerged under a height h. It would be equal to the pressure at the top plus the rho gh. So that's our hydrostatic pressure distribution relationship. What does it tell us? It tells us that the relationship between the pressure, so let's go here, so here it's a pressure difference from the top. It tells us that the pressure is linear with h, so as long as the density and the gravity are constant, the pressure goes linearly with h. So my pressure distribution, if I plot the magnitude, will be something like this. It increases in a linear fashion, and the slope of the increase is rho g. That's the increase of pressure with depth. And now I can do the same thing, but instead I still want to get the pressure at this point. But now what I do is I'm going to pick as a control volume, not the macroscopic control volume I picked from the free surface all the way to the level that I want. I'm just going to pick an elemental, a very tiny fluid element. It does have a weight, it does have a volume, so necessarily it has a weight, and it's a cube that has a dimension dz in the vertical direction, times dx times dA in the other two dimensions. So let's look at my fluid element. This level right here, we're going, so if my coordinate system is z, this level will be z, and the level at the top of my control volume, which is this cube, will be z plus dz. So what are and then I'm going to do a summation of forces in the z direction. Still my fluid is static, so the summation of forces for this fluid element should still be equal to 0, because it's not going anywhere, it's static, no acceleration. So sigma fz for this cube, infinitesimally small cube, dx dy dz, should still be, the summation of forces on it should still be equal to 0. So what are the forces acting on my control volume? I have the pressure at location z at the bottom, that's compressive and perpendicular, acting on this area dA. dA, as you remember, is dx dy. And from the top, we have also the pressure at location z plus dz multiplied by the area. And then we have the weight. So these are the forces that we know, that I can think of. I can't think of any other forces in the absence of magnetic and electric fields that might be affecting my fluid. So I'm going to assume that they do not exist. Only the gravitational field and the pressure from the neighboring fluid elements that are surrounding my cube. So I can write that the P at z plus dz, it's pointing down, plus the weight will be counteracted by P at z plus P at z times dA. And then rearrange, so P at z minus P at z plus dz times dA will be equal to the weight. So the difference in the pressure is counteracted by the weight. And the weight is just the volume. The volume is the dA dz, multiplied by the density gives me a mass, by g gives me the weight of this control volume. I should write it as dW really, but you get the point. And then we're going to invoke Taylor's series expansion. And in Taylor's series expansion, if you have a monotonically increasing or decreasing function, so this is function f of x. So I don't, by monotonically increasing or decreasing function, I do not have any inflection points. So my slope is going in one direction. Then I can, if I have the value of the function f at location x or at value x, so then I can predict what the value of the function at location x plus dx is going to be through Taylor's series expansion, just by knowing the slope and the second derivative and the third derivative. It's an infinite series. So I can predict what the value of the function f at x plus dx. And here my function f is the pressure. So here is my p at z plus dz is just the value of the function at z plus the slope of the function with respect to z multiplied by this little delta z right here, and then you have an infinite series of higher order terms that we are going to ignore. So for the time being, we're just going to substitute with for this term using Taylor series expansion, which gives me dp dz time, or partial p by partial z times delta z. So I'll substitute for this guy. dp dz, I've put it over here and multiplied by delta z, so the delta z goes with the delta z, so I end up with, and the dA goes with the dA. So I end up with dp dz is equal to just minus rho g. And then if I integrate this, in fact I first separate variables. I take the dz over here and integrate the dp, gives me a p, and integrate the dz, because rho g is a constant, the dz gives me a z. And then I'm doing an infinite indefinite integral, so I add a constant of integration, which is p0. And what is p0? It is the value of the function p, of the pressure p, at the origin, at where I place my coordinate system z. So this is my origin. So you have the choice. So typically, like, you want to have a good choice by placing the origin. You have the freedom to place where your origin is, as long as you have z pointing upwards. That's why you get the minus sign. You have the freedom to place where your origin, that is z equals 0, is going to be within the fluid. So you can put it at level 1, level 2, level 3. And a smart choice would be at a level where you know what P0 is. But from this relationship, if I set z equals 0, I get the pressure to be equal to P0. So P0 is the pressure at level at z equal to 0. But let's go, so this is the exact same relationship we got from the previous analysis, from the macroscopic analysis, and except now we have this, the only difference is the minus z. So for us, the minus z is just the h. So we had a rho gh, because h, if you remember, was the depth. So h, we were measuring it from the surface of the fluid, so that was h. And here z, we're measuring it in the opposite direction. So that's why we get a minus sign with the z. So keep that in mind. But intuitively, as you go closer and closer to the center of the Earth, so this is G, that points towards the center of the Earth. As you get closer and closer to the center of the Earth, your pressure is going to, in a fluid, your pressure is going to increase. So keep this in mind. This is the picture you want. Z is in the is in the opposite direction to the gravitational vector. That's how we've chosen it. We could have chosen it differently to be in the same direction. We'll lose the minus sign, but intuitively, as we said, think of it as just minus Z is your depth. So this has implications. So if you go dive down in the sea, the deeper you dive, the higher the pressure, and the more the for the untrained divers, you can face changes to the eardrums and to the pressure that can affect your biological response. And if you go with a trainer, you always do 1 minute, 2 minute, 5 minute checks to say that you're to tell that you're okay, especially as you go deeper and deeper. They check with you every time. It's because the pressure increases as you go down, and that affects your biological response. And same story if you also go in the opposite direction. If you fly in an airplane, you take off, the decompression can affect your eardrums, and same thing as you land from a high altitude. You're going to get your eardrums to be pressurized or pop in. So you have, especially kids, they notice this, and that's because the pressure varies with the Z, with the altitude, with the depth. Let's now look at this picture over here. So here I have water and air, and let's define a free surface as the interface, as the area, as the line, interfacial line between the two immiscible fluids. So air and water do not mix; they're immiscible for all practical purposes. And at that free surface, I know my at Z equals 0, I know my pressure, so I can go back. If I've placed my origin here, I can go back and find my P0 in the previous slide to be the atmospheric pressure at the free surface. So the symbol for the free surface is this triangle with 3 lines underneath it. In the air side, as you go up, so this is just an explanation of the previous slide. As you go up, you're going to experience a depressurization, and as you dive down in the sea, you're going to experience a pressurization with all the implications on your biological response or physiological response. So now we'll do an example. I have a multi-layered fluid right here, oil on top of water, of glycerin and mercury, and I'm interested, and I know the pressure at the top level at Z equals Z1 to be P1, and I'm interested in finding the pressure difference between P1 and P5 at level Z5. So you'll just need to do the difference in pressure between two levels is just the minus rho g Z. So here, where was that? So P minus P0 is the minus rho g Z. And so the minus Z, as we said, is as we go deeper and deeper, we increase in pressure. So my pressure at level 2, so this pressure P2, would be equal to the pressure P1 plus the rho oil times G multiplied by Z1 minus Z2. So in other words, P2 minus P1, so the pressure at level 2 has increased from level 1 by an amount of minus rho delta Z times G. Here Z2, this number is negative, and that's and that's why you get a positive increase. That's negative and that's negative, so this whole thing is positive. So you keep doing all this, and now if you want, so the easier way of doing it is if you just say, well, this is the this was deleted. This is the height of the oil, the depth of the oil, depth of water. So you'll say the pressure P2 is the P1 plus rho oil times G times H oil, and the pressure 3 is the pressure 2, which we've already computed, plus the rho of water times the H of water times G, and you keep adding those rho G times H for each layer of fluid. You sum them all up from the top to bottom, and you get the difference between the pressure at level 1 and level 5. So let's do this example here. Maybe what I should mention, one more thing is to mention here. We learned that pressure varies with Z, that is with depth. So if I'm going horizontally in the X or Y, and my fluid is static, I shouldn't expect any variation in pressure between along the same horizontal level. So that's maybe one conclusion to, or maybe one rule of thumb to stick with. And the other rule of thumb is pressure increases with depth. So, and you don't have to worry about the minus sign and the Z. Take it easy and say, okay, I'm getting closer to the center of the Earth in the direction of G, then my pressure is increasing. I'm going in the opposite direction of G, my pressure is decreasing. So let's do this example. This is a cylinder at that we know the pressure at point A, and we have two fluids, rho 1 and rho 2, and it's open to the atmosphere at the end. And we are interested in the pressure PA or minus P2. So if I follow those two simple rules, if I go horizontally, pressure doesn't vary. If I go vertically, if I go vertically down, my pressure increases, and if I go vertically up, my pressure decreases. And if I go horizontally in the same fluid, my pressure doesn't vary. Then we can find the difference between PA minus P2. So the pressure at A is the same as the pressure along this line until I get to this point, and because I'm moving horizontally. And now if I move vertically, I get the pressure at this level, P1 is equal to P at A plus rho 1G times the delta Z, right? So so I got to P1, so that's PA plus that gives me P1. And if I move within the fluid and get to the exact same height, it's the same fluid, I don't have any obstruction, any solid obstruction, I don't have a pump or anything, still static fluid, it's completely free and open, then I would not expect any change in pressure at a constant level of fluid. So that's still the same P1 over here. So I've already walked through the fluid until I got here, that's P1, and that's what's drawn right over here. Then I would move up, so I would subtract. So now I'm depressurizing, so my pressure is dropping by the amount of the density of the fluid number 2, so minus rho 2G times this delta Z, which is Z2 minus Z1. That will get me to this point, which is P2, which is the P atmosphere that I'm looking at. So it's simple, and I'm sure many of you, or almost Many of you are familiar with this concept, but here we have it. Okay, so let's do a slightly more complex geometry. Still the same story, it's just extra terms. I want PA minus PB, so let me start with the pressure at point A. So I will move horizontally, it's still PA, and then I'll move vertically, PA plus rho G, rho 1 G H1, so which is ZA minus Z1. So you see, I write ZA minus Z1 because here it's a positive number. So I always start, the delta, so if I'm dealing with this going down, your pressure increases, going up your pressure decreases. My delta Z is always positive, so I could just put absolute values around it as I'm dealing with this. So I'm dealing really with the H here. So PA plus rho 1 G times the delta Z, the absolute value of that, which gets me to this pressure. So it's still the same pressure between those 2 points, minus the rho 2G times the delta H between 1 and 2. So in this case, the delta H is Z2 minus Z1 because that's a positive number, right? And you get now to the third fluid because I'm moving through. So I stopped at the interface that allows me to move along the same fluid to the same level. And then I keep going through fluid 3. So now I add, so it's plus because I'm increasing in pressure, and still that Z2 minus Z3 is positive. So you see here I had Z2 minus Z1, and here I have Z2 minus Z3 because Z2 is the higher level. So really I should, to avoid this, I should always put absolute values so as you're not getting confused with this. And then I go up from, so I go horizontally across this level, and then I go up. So it's a minus the rho 4 G times the delta Z, which gets me identically to the pressure PB. And then if I rearrange, I get PA minus PB. Now, these are what we call these systems manometers. The more simple one is the U-tube manometer, is just shaped as a U-tube, and it's a measurement of pressure device. And these were before pressure transducers, electronic pressure transducers were widely available. You really had to make do with a fluid-filled manometer. But nowadays we have pressure transducers or differential pressure transducers that do the same job. So now let's look at a piping system. I have a pipe that has a process. For instance, here has a component. It could be a filter, it could be a valve, and there's a flow that goes through this pipe. And so I'm taking a snapshot of what's going on. It's connected from the left and it's connected from the right, but that's no interest to me at the current time. When you stick in this pressure transducer, the fluid within the pressure transducer, there is no flow. This is more like attaching a voltmeter to a line across a component, and so there is a current going through the component, but across it through the voltmeter. This is, if you will, my pressure transducer being the voltmeter. There is no current, or a very negligible, that it's we can say that there is no current and no flow going through it. So within a transducer, the fluid would be static, it's not moving. So we would be measuring what we call a static pressure. And that's how we implement this So that same story we implemented with a fluid-filled manometer. So I have a pipe right here, and I drilled two very tiny holes. So unlike this system where the transducers are connected through flanges, big flanges, I could just choose to drill a very, very tiny hole here and a very, very tiny hole here, just millimetric type hole, and connect those, two ends of the pipe, the U manometer in there. This is fluid A, it could be water, and this could be a fluid B, it could be oil, or it could be mercury, depending on the application that you are trying to look at. And typically these systems, these flow devices, a filter, a valve, or anything, end up creating a pressure difference, a static pressure difference between across. So it's like a voltage drop across a resistance. So they act like a resistance in an electric system. So you get a drop in pressure, and we can measure this drop in pressure through a manometer. So within the pipe itself, the fluid is moving. Within my manometer pipe, which is the tiny little tube, my fluid is static. So even though this is a moving fluid system, within the manometer itself, the fluid is static. It's not moving, which is great. And then I can find the pressure difference across this device here, pressure at A minus pressure at B, which we call the pressure drop, which is a very important concept in fluid. So that's in the moving pipe. I can find the pressure drop if I go through the manometer. So there is no motion in the vertical direction, so I can take the pressure at A plus this height of the fluid, right? It's a manometer, gets me to the pressure at this point, and which is also the pressure at this point, minus the pressure associated with the rho GH of this fluid, fluid B, minus the rho GH associated with the other leg of fluid A, gets me to pressure B. And that's what we have over here. And the diameter D is the diameter of the pipe, so D over 2 is just, so we're measuring the D over 2 is this distance, and that's the whole diameter is D. So we account for each column of water, D over 2 and L and the H. So you'll when you rearrange this, you'll see that the difference in pressure is equal to this height multiplied by the delta rho, the difference in density between fluid A and fluid B, rho 1 minus rho 2, or rho 2 minus rho 1, times the G. So it's delta P is equal to the rho delta rho G times H. Okay, let's do a quick experiment, and in this experiment you're going to get, let's see here, okay, in this experiment you're going to get a bottle of water and then a container of, and then you're going to take the bottle of water and flip it upside down. So you'll see when you flip it, you're going to pour water in, but now if you get the neck of the bottle into the water, see there is no more flow. The fluid becomes static. Once you get the neck, the bottle, the neck of the bottle inside the water surface. If I just take it a millimeter up, it's actually the flow is going to stop. So we are interested in analyzing, so this fluid is static, and we are interested when it is sitting like so, fluid is static, and we want to analyze it and understand what is going on, what are the forces that prevent this volume of water from flowing down into the pool that's beneath it. Okay, so here is a schematic of that upside down bottle. So these are the black lines are the walls of my bottle, the plastic bottle. And here I should probably, to be more accurate, I should probably draw a neck, but it's not necessary. So we could just draw a neck over here. So you get the idea. And the bottle is upside down, so it's pointing in the towards the center of the Earth, and I've picked my Z coordinate system to be in the opposite to G, so it's pointing upward. The height of the fluid is H in the bottle, so up until it touches the water of the so measured from the surface of the water. So I got two free surfaces. I have, if you look at the previous slide, anyways, you get a free surface here, so you get a gas pocket because we lost some water here, and I got, so that's air-water interface, and I also got a free surface here, another air-water interface. And I would take the water inside the bottle that's just right above the free surface, because that's the confusing part of it. Why is the water not flowing? Why am I able to sustain a level of a level H of water above the free surface without it flowing? So it makes sense to study this volume of water. So I pick it as my control volume, and I would like to understand why it doesn't flow. Why does it not move down? So I would like to understand what happens in the Z direction. So it's static, so I would do a sigma f z for this control volume. Now this volume has a volume of the volume of this control volume is the area A, the cross-sectional area, times the height h, and then I have the p atmosphere. The pool of water is open to the p atmosphere. So what are the forces acting on my control volume, on my red control volume here? Well, I have its weight. That's the natural one. Weight is pointing downward. Then I have, as you guessed it, right, this imaginary line that I've drawn here is in touch with the fluid at the bottom, and the fluid at the bottom acts on my control volume because it's a static fluid, only by a pressure force, not a shear force, by a pressure force, and that pressure force is compressive and perpendicular. So compressive, pointing towards the surface, and at 90 degrees. Same thing on top. I have air in touch with my control volume, so I get the pressure of the air, which I'm going to call P top, and that's P top times an area that gives me a force, and the bottom pressure times an area gives me a force. So these three forces, P top times A and mg and the P bottom times A, balance out. That sigma f z is equal to 0. So then what is the mass? We said that the mass is just the volume, the area of the cylinder multiplied by the height, and then you multiply by rho, you get a mass, and then by g you get a weight. So that's your weight. So that area right here cancels with this area and cancels with this area. So the difference between the top and bottom pressure is just equal to the hydrostatic pressure rho gh. And now let's look at the bottom pressure. What is this bottom pressure that we're looking at? Okay, so we all agree that the pressure along this line is P atmosphere. Let me take a line, a horizontal, so whether at this point it's P atmosphere or at this point it's P atmosphere. And let me take a line over here. I can tell you from what we have discovered in the previous slide that the pressure at this point where my mouse is equal to the P atmosphere plus
Yes, you guessed it right. This length L, rho GL, P atmosphere plus rho GL. So if I go horizontally, the pressure at the opening of my bottle is still P atmosphere plus rho GL, right here. And if I climb up within the bottle, it's still the same fluid, and there is no solid element. Still, it's the same fluid. It's an unobstructed path of fluid. So I get P atmospheric plus rho GL minus rho GL. So I end up with P atmospheric here. So at this level, still the same fluid, just like a manometer, if you think about it. The pressure here, the P at the bottom is just P atmosphere, which is what we have over here. So let's plug it up into this equation. P top is the atmospheric pressure minus rho GH. So what this tells us is that the gas pressure right at the top is equal to the atmospheric pressure, which is outside the bottle, minus this the pressure associated with this column of water. And what that really tells me is that by flipping the bottle, and I have created somehow a vacuum here. I've created a region, a gas, that's at a pressure below the atmospheric pressure by a vacuum pressure of rho GH. So it's the pressure in the gas compartment here, closed gas compartment here, is below the atmospheric pressure. It's under vacuum. And then the natural question becomes, how high can my bottle be? What do you guess? 1 meter? We can get to 1 meter of, if I get my bottle to be 1 meter, would it still hold the water? Can I get it to 10 meter or 100 meters? So let's see. So let's check this H. What is H max that we, so rearrange, you get H is the difference in pressure divided by rho G. The top, bottom pressure, the bottom being the atmosphere. So P atmosphere minus P top over rho G. And what is the H max? Let's see. Rho G is a constant. The P atmospheric is sort of given. We live on the surface of the earth. That's what decides it. So it's around 100 kilopascal. So how high I can get, what is the maximum H, is decided by this top pressure. And what is in this gas pocket here at the top? Well, there's gas. And what is the absolute minimum pressure I can get my gas to? Well, if I can get to absolute vacuum, so ideal gas low, if my mass is 0, no mass of gas at all, so I can get to 0. So absolute minimum, or the absolute minimum P top is going to be 0. So my height will be equal to the P atmosphere divided by rho G. So it's the column, the height would be the height of a column of water that's equal to the atmosphere. But actually, it's in practice, it's actually going to be slightly less than this H max that we have found. So the actual H max is actually we're not going to be able to get down to this zero pressure, absolute zero pressure, absolute vacuum. Primarily because the water will kick in here and will start evaporating and filling the gap. So we're not going to end up with a zero mass gap. It's going to be filled with water vapor. And can we get what this water vapor pressure is? Of course, you go to your thermodynamic tables and you find the room temperature and you get the vapor pressure at that room temperature. So if I am at 25 degrees C, I'm going to get to 3.2 kilopascal. So when you're at sea level at 100 kilopascal, your water boils, so it transforms from liquid to gas. You need a temperature of 100 degrees C. But if you're sitting in a vacuum chamber of 3.2 kilopascal, you only need to raise the temperature of your water to 25 degrees C to make it boil. And that boiling is what we said is the water transforming from liquid to gas. So here kicks in our thermodynamic pressure again. You see, remember we said it's the thermodynamic pressure can tell us the state, whether it's a liquid or a gas. So here's an application of it. So stick in this 3.2 kilopascal, and let's have a good estimate of P atmosphere to be around 98 kilopascal. So I end up with 95, that minus that, 98 minus 3 is 95, divided by the rho g. So I'm going to get around 9.5, 10, between 9.5 and 10. So it's 9.7 meters here. And that has actually, that comes pretty much from the properties of the water, and it comes from the atmospheric pressure where at that particular location that we are at, as well as the temperature, the properties of the water at this particular temperature. And the implications of this height is that if you want to draw water with a pump, you can't get the suction side at a level higher than 9.7 meters. You're going to get water to boil. So if you draw a well that is 50 meters deep into the earth, and you place your pump at the surface of the outside the well on the ground, and you take a pipe, the suction side of the pump, you stick it down, take it 50 meters, stick it down into the well, you turn the pump on, you're not going to get anything. Even if you prime it, whatever you do, that's not going to happen. So what you do, if you have a well that is above 9 meters, you have to actually go dive down. That's why you use submersible pumps. So submersible pumps are designed to address this particular issue of water boiling. We don't call it boiling, we call it cavitating, because we're not adding heat, we're just changing the pressure to induce a change in state in the water, a thermodynamic state. Okay, so the atmospheric pressure is actually an important quantity that now seems to be affecting our industrial processes, and we would like to look at it in some more. So I've discussed this with you, but very briefly I wanted you to do a take-home experiment. That's another demonstration, the exact same story, the exact same analysis as what we have just done. Take a, let's see if this works. Take a glass of water, piece of paper, and now put the piece of paper on top of the glass of water and flip it. Let's see. So yes, you've got here cardboard. Here I have a sort of more like a thick piece of paper, cardboard, and put it on top. There is no glue or anything. There's no magic in there. It's just atmospheric pressure. Now flip it carefully, that is, so you can make a mess, so you have something underneath, so just in case you have an accident. So you see the piece of paper, once you take your hand out, actually carries the weight of the water. And what the piece of paper does is just separate the two systems, the atmospheric air, the liquid in the glass, and the glass as well as the gas pocket at the top. So the gas pocket at the top actually has a negative pressure. The atmospheric pressure is acting from the bottom, and the difference between the atmospheric pressure and the negative gas pressure is what accounts for the pressure associated of this column of water right here. So it's the same story, but those two stories come to tell us that the atmospheric pressure is important, and we can see its effects in our lives, in our industrial lives, professional life, every once in a while, particularly if you're working with pumps and piping systems and so on, which many engineers do. So the atmospheric pressure is it's kind of important. We want to look at it and at its origin, and its behavior a little bit more. So this is what we want to start talking about in the next lecture. That is the atmospheric pressure variation within the Earth's atmosphere. So I will stop here. Thank you for your attention, and we will continue in over the next lecture with the atmospheric pressure.